Another example with static rigid bodies. This time we have a ladder resting on a wall. So we've got a ladder of mass m and length 3a resting on a rough horizontal ground. So we're going to have a reaction force at A. We're also going to have friction. Let's see what else is probably going to act towards the wall, but let's read the rest of the question. The other end rests on a smooth vertical wall, so there's only a reaction force perpendicular to the wall. No friction there. A load of mass 2m is fixed to the ladder at C, so let's write 2mg here. It's our force. The ladder is modelled as a uniform rod, so mg is acting in the centre. The ladder rests in limiting equilibrium, so our friction is acting towards the wall and is going to be its maximum value. Find the coefficient of friction between the ladder and the ground. So we need to work out the reaction force at A and the friction at A. Okay, so we're going to need to take moments, and that will allow us to find the reaction force at B, which will subsequently allow us to find the friction at A, and then we can resolve vertically to find the reaction force at A. So we need to do both of those things. So let's take moments at A first. Remember, when you take moments at a point, any forces at that point do not create a moment. So my clockwise moments are going to be from the mass that's at C, so 2mg times this distance, which is A cos 60. So 2mg times A cos 60 plus the weight of the ladder, mg, times this distance, which is 3/2a cos 60, because it's half of the whole ladder. So let's just tidy this up. We've got cos 60, which is a half. So we've got a half of 2mga, so that's just mga. And then we've got a half of 3/2. So that's 3/4 mga. 3/4 plus 1. So we're going to get 7 GA/4. Okay, and then our clockwise moment is created by the reaction force at B. So we need this perpendicular distance. That's how far it is away from the point A. If we were to carry this force across, so we need that length there. So that is the opposite side of this big triangle that's created by the ladder and the wall and the floor. So it's going to be 3a times sine 60. So we're going to get the force, RB, times 3a sine 60. Now sine 60 is √3/2. So we're going to get 3√3 RBA/2. So those two things are equal to each other. So let's make a little equation. 3√3 RBA/2 equals 7mga/4. Okay, both things are being multiplied by A, so let's get rid of those. We can times by 2 and divide by 3√3, so we get the reaction force at B is 14 mg over 12√3. And we can divide top and bottom by 2, so we get RB is 7 mg over 6√3. So then if we resolve horizontally, we will get that the forces to the right, the friction, must equal the forces to the left, the reaction force at B. So therefore the friction is also 7 mg over 6 root 3. And then resolving vertically, forces going up, which is the reaction force A, must equal all the forces going straight down, which is 2 mg plus mg. So the reaction force at A is 3 mg. So if we're in limiting equilibrium, that is when the friction equals mu r. So therefore mu will equal friction over the reaction force. So mu equals 7 mg over 6 root 3 divided by 3 mg. So we get all of the m's and the g's cancel, and we can put that into our calculator. 0.225 to 3 significant figures. Then part B just says state how I've used the assumption that the ladder is uniform. What did we do with the fact that it was uniform? Well, the fact that the weight appears to act in the center. Obviously, if it was a non-uniform rod, then it would be acting at a different point, and that would change our values. The assumption that the ladder is uniform, that the weight acts in the center, okay, or the center of mass is in the middle of the ladder.